in which we hack our way to extracting more features than advertised. Welcome back to the MVPN video series. In today's video, we will configure MLDP in-band signaling or Profile 6 on iOS and iOS XR devices. If you're looking for an introduction to MLDP in-band signaling as well as the details of its inner workings, the previous video in this same series will be the one you want to view first. So let's begin. Now, what are the prerequisites and then what are the actual required configs? So as is the case with all of our MVPN profiles, VPN v4 must be working completely between all the sites. Now, the reasons for this have been covered in the previous videos, but essentially this is the table that would be used for the RPF checks of the MVPN. So it is essential that all of the routers have all of the CE sites have reachability to each other, and all of their relevant IP addresses are in the VRFs of each of the PEs, because that's what the RPF check is based upon. The second prerequisite here is that MLDP must be functional on all of the core devices, and it should be ready to signal all of the P2MP LSPs end-to-end. Now, this is something that happens automatically on iOS, and on iOS XR, it's just a couple of commands. So we will make sure if those commands are on the devices already or not. So finally, what do we need to do to configure this? So we have to configure CPIM within the PE-VRF. So once again, this is a prerequisite, but this is something that has already been done in our network in order to save time. So you should have that CPIM adjacency between all of the PEs within the VRF and the CEs globally. The second thing would be you have to configure MLDP in-band signaling as the forwarding technique for the MVPN for the VRF. On iOS and iOS XE, these are a couple of global commands, so it's not very logical, or at least as logical as it is on iOS XR. But essentially, you would start MPLS MLDP in the IP multicast. So that process for the VRF has to support MPLS MLDP. That's the first command. And then you would issue the IP PIM VRF MPLS source command. So name of the VRF, and then what is going to be the source of these tunnels or source of these point-to-multipoint LSPs. So once you configure both of these commands, the rest of the stuff is a matter of troubleshooting. On iOS XR, number one, do not forget the RPF fix-up. So, and I repeat that twice, so do not forget the RPF fix-up. So by default, the RPF checks are always against the PIM core tree. So you have to change that, or you have to at least add the MLDP in-band signaling core tree to a policy and then use that for the RPF check within PIM. So we'll make sure that we are doing that. The other part is actually quite a bit more logical than iOS. So you would go into the multicast routing process, you would go inside the VRF and address family IPv4. And then essentially you do the two things that you did on iOS or iOS XE. So you choose the source of the point-to-multipoint LSPs, and you'd say that the MDT now is going to be in-band signal. So MDT-mLDP in-band signaling IPv4. Once you issue those commands, you should be good to go. Before we begin, there are a couple of caveats about this particular topology. So in order to show you that little hack that I talked about where ASM is somewhat unofficially supported with XR, I needed two XR routers to demonstrate that. So what I've done here is R4, which used to be an iOS router, has now been replaced with an XR router. The other things that I've done or the source and the RPs, etc. are now indicated on the topology. So let's take a look at the source. The source is always going to be 10, 10, 10, 10. So we'll source the pings off the loopback of router 10. Now I say the RP is variable here because we will change it to suit a couple of our scenarios. And I'll talk to that particular reason when I get to it. Now, the receivers are going to be R9 in site 21 and R7 in site 1. So let's take a look at R7. They're both joining the same sources, but they have different IPs. So R7 and R10 are both joining an SSM source. So that is 10.10.10.10, 232.10.10.10. So that's the S, G source. They're also joining an any Source Multicast group, an ASM group, and that's the star, 239.10.10.10. But in both of these cases, their RP information is different. So they have a local RP in the site. So in case of site 1, that is R6. So that's the RP for site 1. And I believe this is using BSR to get this information across. So R1 knows about this and R7 knows about this, because technically, in R1 inside the VRF, of course, but technically all of those are site 1 routers. Similarly, for site 21, we have picked R8 as the RP, and there is static mapping on all of these routers. So you have static mapping on XR1, R8, and R9. So they're functional within their own domains. And that's one of the major problems. Remember, there is no CPIM within these sites, right? So they only run, or between these sites is what I should say. Within the sites, there is CPIM, but between the sites now, we are going to use MLDP. So we cannot rely on something like BSR. So in case, even if any Source Multicast gets supported someday, I believe one of the only ways to do this may be static RP mapping or something other than BSR or auto RP learning. So remains to be seen. I haven't really taken a look at, because it's not really supported just yet. I'm not sure what the RFC says about it, but static mapping is something that almost always works, so it should work in this case. And in our particular case, we have done static mapping at one place and BSR at the other place. Now, when we go to site 4 and we change the RPs around, they are almost always going, not almost always, they're always going to be statically mapped. Because once again, there is no way I can get BSR, at least that I know of, across the SP core to go to XR4 and then go to site 4. So they would have to be statically mapped. These mappings are already here. So let's go ahead and look at the mRoute tables on R1 and XR1. That's how we'll begin. And after that, we'll start configuring. So let's look at R1. And actually, before I go on R1, there is one thing that I neglected to mention, and that is source-specific multicast. So source-specific multicast, or SSM, is configured for all 3 of our client sites. And it is only configured for the default group, which is 232/8. Now, if you remember, on iOS, there is a special command that goes for that particular group. And on iOS XR, it just supports it by default, that particular group, 232/8. When I say site, I also mean within the VRF of the PE, because that's technically part of the site. So it's configured at all of those places. Now, knowing that, what should we expect to see on R1? So if you think about the star, G tree, the star, G tree terminates at the RP. So if it starts from R7, it should literally just end at R6 and not go anywhere, because there are no sources yet. For the S, G tree, it will try to find its way as far as possible towards the source. So in this case, the source is 10.10.10.10. That's on the other side of the SP core. So what I should expect to see is probably a state for 10.10.10.10, 232.10.10.10, that S, G. And I should see an outgoing interface towards R6, but I shouldn't really see anything in the incoming interface. Why? Because the tree, basically, the PIM domain is terminating at R1, and there's no MVPN to connect it yet. So there's no in-band signaling, there's no overlay, there's nothing there. So in this case, let's quickly take a look. We'll say do show IP mRoute VRF C1. And that's exactly what you see. So you see 10.10.10.10, 232.10.10.10, that's in S, G. And as I said, the IIF is going to be null because we don't really know how to get there on a multicast enabled interface yet. The outgoing interface obviously is 2.16. We should expect to see something similar on XR1. So just for completeness sake, let's go and take a look at that. We'll say show PIM VRF C1 topology. And we see something similar. So we see 10, 10, 10, 10, 232, 10, 10, 10. And we see an outgoing interface. So there's something in the oil, but there is nothing in the incoming interface. So we really don't have that tree built yet. So let's go ahead and follow our steps and configure MLDP in-band signaling first on R1. So on R1, we will say IP multicast. And this is where you have to either look at the documentation. I'm fresh because I've been working on this, creating this presentation. But this is something you are liable to forget. It's not very logical, and it's two different commands that are in two different hierarchies, really. So IP multicast and IP PIM. So I would say look at the documentation while you're doing this, in case you forget. So for now, it's going to be IP multicast VRF C1. And then I'm going to pick MPLS, MLDP, and that's it. So that essentially starts the in-band signaling. But remember, there's one more thing. I also need to have that source interface for those point-to-multipoint LSPs. So in this case, it's going to be IP PIM, and that's that different command, VRF C1. And this is again MPLS, source, and then you pick the source. In our case, it's going to be loopback 0. Once this is done, you should start seeing some logical interfaces created, and you should start seeing some MLDP activity. So essentially, what MLDP is doing right now is it's going to start signaling a point-to-multipoint tree. And it is going to signal that point-to-multipoint tree towards R10. So what is the shortest path towards R10? It looks like we have two paths. We can either go towards R2 or we could go towards R3. I don't frankly remember the type breaking process on iOS, or for that matter, iOS XR. So let's take a look at how that tree was created. So in this case, I'm going to say show MPLS MLDP database. So as you can see, we created a point-to-multipoint LSP towards the root, because guess how we are going to determine that root? The source. What is the next hop for that source? That's where the root is going to be built towards. So in our case, that RPF check is going to take place within the VRF. So let me see if there's an RPF command for this. So if I say do show IP RPF VRF C1 for 10, 10, 10, 10, there is no route. Select, nope. So is it IP PIM RPF? Nope. Yeah, so there used to be a command here, but it's not working. But let's just look at the routing table within that VRF, right? So we'll say do show IP mroute, or do show IP route VRF C1 for 10, 10, 10, 10. And now you can see it is known via BGP, so it's coming via VPN v4, and that next hop is 4444. So even though that IP RPF command didn't work for me, I don't exactly remember why it's not working, but this is another way of checking that out. So 4444 then becomes your root. Let's go back and take a look at the MLDP database. So that's how we picked our root. We picked our root as the next hop towards 10, 10, 10, 10. And in the opaque value, and now this is where in-band signaling is completely different than, for example, MDT-mLDP, where we were just creating a manual multipoint to multipoint LSP, and that was based off the VPN ID. In this case, in the opaque value, you can see it's a VPN v4 route. Here is the RD 4444:100 because, well, that is the RD. But if you do want to see, we could say do show BGP VPN v4 VRFC1 or VPN v4 unicast VRFC1, and now we can say 10 10 10 10. And in this case, if you look at the RD, it is right here. So 4444:100. So that's the RD that is being mapped into the opaque value. So here's the RD. Here's the local source, right? So this is the S, G information. That's packed right in there, and then they basically create an opaque value out of it. So now you can actually see how the signaling is taking place using MLDP, and we don't really need PIM anymore. But what I really wanted to see was who was going to be the upstream. So the upstream here is 2222. So whatever is the type breaking process here, it's only going to pick one, and it's going to pick 2222. So let's get rid of this 3333. And 2222 is going to be the next hop. And from 2222, it's easy because it only has a single best path to XR4. So it's probably going this way over to XR4. Now, XR4 is running MLDP. No, actually, it is not running MLDP because it's an XR router, and I probably have not configured it yet. Anyway, let's go to R2, and then let's go to R4 to see what's going on there. So on R2, we issue the same command, do show MPLS MLDP database. And this time, again, it's the same LSP that was signaled from R1. The upstream client is 4444, so no real shock there. The replication client is downstream, that is 1111. So let's go to XR4 and look at the MLDP database. Do show MPLS MLDP database. So it has that. It has terminated the P2MP LSP, but the thing is, has it really used that information to? And I want to check one thing. Maybe I did configure MLDP on here. So if I say do show run MPLS, I have configured MLDP on it. And just for consistency, let's go ahead and do it on XR1 too, because I frankly do not remember if I did it here. So show run MPLS. And it is here as well. So MLDP is at both places, but this is a simple command. Do not forget to issue it. So you would need this command for that P2MP or MP2MP LSP to work. That hasn't changed from the profile 0 or profile 1 days. So on XR4, we are terminating the P2MP LSP. So the mapping seems okay, but what about the signaling? Did we populate the multicast routing table with this? Well, there's only one way to know. So do show PIM topology VRFC1, or actually it's going to be show PIM VRFC1 topology. And we haven't. And the reason for that is we need to configure in-band signaling plus the RPF check to start using these states. Right now, I'm not configured to use the signaling that is coming through the LSP. So no time as good as right now to go ahead and just configure this. And in this case, I can actually do it just logically because it is pretty logical to configure on XR. So it starts with multicast routing inside the VRF. So that's where we were. Now, what is the next thing? I would think it should be the address family, right? So address family IPv4, now I'm in there. And now I have access to the MDT commands. So once I have access to the MDT commands, that's what I'm going to use. So I'll say MDT. This is going to be MLDP. And there, see, it actually uses the words in-band signaling. Whereas if you realize on R1, if I say do show run include multicast, there's really no way to tell if this is in-band signaling or not, right? So XR, you can obviously tell I like the config a little bit more on XR for this particular profile. So MDT-mLDP in-band signaling for IPv4. And that's it, that's the command. The other command again is the source command, and that's also configured with the MDT keyword. So we would say MDT source loopback 0, and that should be it. Let's commit this config. And let's see if that state populated, right? So we'll say do show PIM VRF-C1 topology. And that state still hasn't configured. So remember, what did R1 do? R1 created, and it's not very obvious here, but if I look at the mroute table, so on R1, if I say do show IP mroute VRF-C1, I can actually see that now there is an IIF, and it is the same format IIF. It is an LSP virtual interface. It's 1 in this case. That is used as the IIF. So there's a logical interface there. And this logical interface should be part of the PIM process because PIM has to have that interface in its process so it can create those states in the multicast routing table. So if I say do show IP PIM VRF-C1 interfaces, I am seeing that interface here. There's also this LSP VIF0 interface, which I'm not 100% sure about what its functionality is. But for LSP VIF1, I definitely have an interface there, and it's in the PIM VRF process. Now, those who have worked on XR before and those who have worked on MVPN on XR before, you probably already know where I'm going with this. If I say do show PIM VRF-C1 interfaces, I do have an MDT interface. So again, I believe this is something like group in-band signaling, but I don't remember the full form of it. But there is a logical interface for VRF-C1, but guess what? PIM is off on it. And if you remember how to turn PIM on it, it's a clever little thing that you have to do. And it may not be very obvious, even from the documentation. You actually have to start PIM on the global, on the interface that you're using as the MDT source. So it's as simple as that. So in this case, we'll have to say multicast routing. And again, this is the global routing table. So keep that in mind. This is not the VRF bounded routing table. This is the process, but it is the global process. Multicast routing, address family IPv4, interface, or actually let me enter here and I'll say interface, loopback 0, enable. Once I commit it, I hope to see a little bit better output on the VRF interfaces. And now you can see PIM is on it. So this is a little quirk of XR. Even though you're not running PIM globally, you're just doing everything with MLDP, you still have to start the multicast routing process on it. And usually we do that to bring it into the PIM process. But again, this is what you have to do. You have to sort of remember this. But if you do it enough times, you shouldn't have any problem remembering this. Now let's go back to the root and let's look at the PIM topology. So do show PIM VRF-C1 topology. And now what's happened here is I've been able to use the information that was inside that MDT FEC, or MLDP FEC in fact, and I've been able to populate my routing table with it, the mrib with it. And in this case, I have an outgoing interface, which is this MDT-C1 interface. And again, I believe this should be inline MDT-C1 interface if I had to take a guess. But whatever, it's a logical interface that ties the two processes together. And I further sent the join on the incoming interface towards R10. So whatever is my interface towards R10, and again, the realm is very important, right? So once you reach the PE, the realm changes back into IPv4. So this is IPv4, and it's going to go towards R10. So now if I look on R10, if everything is configured correctly, which is, not always guaranteed, on R10, I should see the S, G tree all the way completed. So if I say do show IP mRoute on R10, you can see I have this S, G tree. The incoming interface is the loopback 0 interface. The outgoing interface is towards XR2, and then from on and on it goes from there. So what XR4 has done is it has received the signaling data via MLDP, and it has converted it back into PIM, just like we talked about. And before we finish this, actually we can test out the pings even right now. So let's go ahead and test them out. And once again, with iOS, sometimes that first ping has to just be from the normal ping line. The long format ping just doesn't work for it sometimes. So I'm not going to take a risk. I'm just going to say ping 232.10.10.10. Source or loopback 0. Let's send 5 pings out. So in this case, it's going. And there we go. So it is going all the way out, and everything is fine. Now, for the curious, there is the RPF check issue. So why didn't the RPF check mess with this? Well, think about the directionality of the traffic. The traffic, so if I was to mark the traffic in red, the traffic is going out this way. So really there is no RPF issue yet, because the RPF issue would be for the traffic coming in this way, and that would be received on the wrong tree. So for now, we really don't have to do anything about the RPF, and I'm going to leave it unchecked. We'll just create those policies together, because remember, what is the next router that's going to be configured? It's going to be XR1 down here. And when XR1 gets configured, then the directionality of the traffic is going to be this way. And now you would see that RPF problem. So let's go ahead and configure XR1. And in this case, it's going to be, again, pretty simple. We'll say multicast routing VRF C1, address family IPv4, MDT, mLDP, in-band signaling. Or is it in-band signaling? IPv4. And what was the other command? That was the source. So MDT, mLDP, nope, MDT source, loopback 0. And once I say commit, actually no, let me just finish the whole thing. So we also need to bring that loopback interface in the global multicast process. So let's do that now. We'll say multicast routing address family IPv4 and interface loopback 0 enable. And once I commit this here, we should now be able to provision that P2MP LSP towards XR4. Let's see if we were able to do that. So we'll say do show MPLS MLDP database. So there's no entries in the MLDP database. And did I commit this? I did commit this. So let's take a look at the multicast routing again. Do show run multicast routing. So I seem to have everything here. Let me look at my the PIM interfaces, right? So we'll say do show PIM VRF C1 interfaces. It looks like those two interfaces are there. The PIM is on them, so everything looks good here. And the final thing here is going to be do show MPLS, nope, do show PIM topology or PIM VRF C1 topology. Here is the problem. My RPF is still null. And why is that? Because again, for the RPF policy, I can't even send the join yet because I'm not using the correct core tree. So let's go ahead and let's configure the right policy. And if you remember from the earlier lectures, it's going to be a route policy that is going to set the core tree, and then we're going to associate it with the PIM process. Let's give this route policy a name. I'll call it RP RPF VRF C1. Or let's keep it simple, RP RPF C1. I'll say set core tree And we used MLDP default before, but this time we'll say MLDP inbound. And before I commit, let's apply this policy to the PIM process. So we'll say router PIM VRFC1, or router rather, PIM VRFC1, address family IPv4, and this would be RPF, topology, route policy, and the policy that we created. Once I commit this, let's see if that does the magic for us. So we'll say do show MPLS MLDP database. And now, as you can see, I'm sending the same value out, although it shows the RD in a little bit of a weird format, but basically it's the same thing. So it's the same information that you saw on R1. It is being sent towards XR4. And if you realize, it's the same P2MP LSP, isn't it? Because it's P2MP, the root matches, and then the VPN, the opaque ID should or the opaque value should also match. So essentially what we should see on XR1 now, and I don't want to forget, so right after I configure the RPF policy on XR1, what we should see is a single P2MP LSP with two legs, one going towards R2 and the other one going towards XR1. So on XR4, actually on XR1, I want to do a couple of things. I want to cheat. So I'll say show run route policy RPF C1. So I'll copy that and I will put that, I'll copy that and I'll paste it on XR4, and I'll also copy the PIM process. So I'll say do show run router PIM, and I think everything that I need is actually right here. That's all I need. So actually there's an easier way to do this on XR. So if you say do show run formal and then router PIM, then you can essentially just copy this particular line and paste it onto XR4, commit, and now we don't really have to worry about anything. The directionality of the traffic, although I don't think in my particular case, because the source sits behind XR4, it's going to bother us. But, you know, it's fine now in both directions if it needs to be. So let's go ahead and look at the MLDP database here. We'll say do show MPLS MLDP database. And as I told you, there is no upstream neighbor because we are the root, but we have two downstream clients now. So we have an LDP client, which is router 2. That's the branch towards R1. And now we have a brand new LDP client that is towards XR1. We are directly connected after all. So it is this signaling that is being reflected in the MLDP database. So all of that is now configured. So what we should be able to see if we follow the traffic is that the traffic should now be able to go to R8 and also towards R9. And the traffic was already flowing this way towards R1, onto R6, and over to R7. So for every single one of the pings, and again, remember with the short form ping, I always end up sending 2 packets if I'm using a loopback interface. But for the long form ping, I should essentially receive a reply from 9999 and I should receive a reply from 7777. So let's go ahead and send those pings again. And this time I'll just send 3 so I can test it with the long form. So far it looks good, I must say. So now let's send the long form ping. We'll say ping, protocol is IP, the target IP address is 232.10.10.10. The repeat count, let's say 10. Datagram size is fine, 100, timeout is fine at 2 seconds, extended commands, yes. And we want to send it out of gigabit Ethernet 2.1022, that's the interface between R10 and XR2, time to live 225 is fine. And loopback 0 is the source interface that I want to use. Everything else is default. And now we should essentially see 1 packet go out and 1 reply come back in. So I'm reaching all the way out to 9999, and I'm reaching all the way out to R7. So SSM, this is completely working. So now let's talk about the scaling issues that we talked about in our foundational lecture for this. So the scaling issue here is going to be, there is going to be one MLDP that is going to be one LSP that is going to be signaled per group, because the signaling is carried in the FEC. There's no way I can aggregate this. So for every single S, G group, no matter if it's taking the same path or not, because in our little network here, it's always going to be the same path. But if from behind R1, for example, on R7, I join, let's say 4 more groups, what should then happen is I should see 4 more point-to-multipoint LSPs. So let's go ahead and check this out. Let's go on R7 and let's join more groups. So it's going to be on interface loopback 0, and let me join 4 more groups. So I'll join IP IGMP join group 232 11 11 11, and this source is going to be 10 10 10 10. So all of them are going to have the same source. Let's have 12 12 12. That's the second group. 13 13 13. That's the third group. And finally, let's have 14 14 14. So 4 groups joined. Let's go ahead and see on R1 what is the mRoute table look like. So on R1, I'll say do show IP mRoute, and that's VRF C1. So now you can see I have 10, 11, 12, 13, and 14. In total, I have 5 groups from 10 to 14. But what about the MLDP bindings, right? So do show MPLS MLDP database. So as you can see, already the database is expanding. Let's look at the summary view of it. And that shows me that I now have 5 P2MP LSPs. So on these P2MP LSPs, if I say, let's try to figure out, I want to look at the opaque decoded, and then I want to look at the upstream client. So if I say show MPLS database, include opaque decoded, and let's take this 2222. Well, that 2222 is not there. How about if I put it like this? Without a space. Nope. So obviously I'm doing something wrong here. What about the keyword active? Okay, so now you can see all 4 of those, all 5 of those P2MP LSPs are taking the exact same direction. Actually, no, they're being load balanced. So I was wrong there. Some of them are going over 3333, some others are going 2222. So again, it's not load balanced, it's load share. It's probably following the Ceph path for it, whatever is the tiebreaker there, because I have ECMP. But ultimately, every single S, G state is generating a brand new P2MP LSP. And that is the big scalability problem with this particular solution. So for SSM support, that was all there is to it. Now, that brings the end to the official video, right? So anything that happens from this point on, it's all going to be ASM. And it's all going to be completely unofficial. We're going out into the wild. So if all you want is the official support, that's all you wanted to know, feel free to stop the video now. I really thank you for joining us, and I hope you stay tuned for our next video. But if you really want to see some other wild stuff, hang around. So if you've decided to hang around, all, the 2 of you or 3 of you who are still watching this by now, that means you're a glutton for punishment. So let's go ahead and let's try to think about some of these issues and how how can we still make this thing work? So some of this connectivity has nothing to do with profile 6. Some of this connectivity has just to do with the way PIM behaves. And a lot of that magical connectivity happens when the RP happens to be co-located with the receiver. So for example, what I'm going to do right now is I'm going to try to connect site 1 to site 4. And one of the things I cannot do, there is no BSR, there is no auto RP learning right now. So what I would have to do is on XR2, R1, and XR4, I would have to go and have them share the same RP as site 1. So they would all have to be RP 6666. So let's go ahead and statically program that IP in there. So that's going to be R10. So let's go ahead on R10. And this is going to be a simple command. This is IPPIM RP address and then 6666. On XR2, this is going to be under the PIM process. So I'll say router PIM address family IPv4. This is still global. So it'll just be RP address and it'll be 6666. Now we'll commit this. And finally on XR1, this is going to be inside the VRF, but it's still the same command. Actually, this is not XR1. This is going to be XR4. So on XR4, this is going to be under router PIM VRF C1. Router PIM VRF C1 address family IPv4 and then RP address, and this will again be 6666, and I'll commit this config. So now all of them have the same RP. Before we begin, before I explain what's going on, let's just try to ping 239.10.10.10 from R10 and let's see what happens. So again, I won't send the long form ping yet. The first ping, I usually like to just send this short form ping. So source loopback 0 and then repeat, let's say 5. So some packets should go out. Let's see what happens here. And there we go. It seems like it is working. But what you will realize is that there is really no complete multicast tree. So for example, if there was a complete S, G tree all the way from R7 to R6. So if there was a tree that was going this way, from R7, it should go this way and then somehow across the core and then over from XR2 to R10. That means on XR2, we should see an S, G state. What you will find is there should be no S, G state on XR2 because this is not PIM connectivity. This is just some magical stuff that's happening, which we'll explain. So if I say do show PIM topology 239.10.10.10, you'll see that there are no table entries found. The same thing would be true for the entire site 4. So on entire site 4, the other router is XR4. So if I say do show PIM VRF C1 topology 239.10.10.10, there are no entries found there. So what is happening here? What really is happening is the PIM unicast register message is doing the trick for us here. So what do we have to do for multicast? Where is the break? The break is in the SP core. So somehow if we could tunnel our traffic across the SP core, then we would have connectivity. So in this case, what's happening is when R10 sends that first message, it's also the DR, right? So from a PIM point of view, it is also the DR. And what does the DR do with the very first message? So for example, to register itself with the RP, it is going to send a unicast message. And that unicast message is going to just send across the core, tunneled and unicast packets. So with a unicast source and a unicast destination, but with the multicast packet tunneled inside that register and is going to send it to R6. R6 is going to decapsulate that packet, and it is going to send that multicast packet to the final destination, wherever is the star comma G oil is. And in addition to that, it should also begin the registration process to the S comma G. So it should start sending an S comma G join up here. So let's make sure that that is what is happening. So on R6, we should have a star comma G because it happens to be an RP, and that's the root of the star comma G. So on R6, and looks like we previously did a verification there, but we'll say do show IP mroute and 239.10.10.10. So right now on the star comma G, there is no incoming interface because the RP happens to be the root, but there is this outgoing interface list, right? But on the 10.10.10.10, there is an incoming interface. There is an incoming interface because essentially what R6 is trying to do is it is trying to join that S comma G tree, and it is sending that join towards R1. So R1 should now also have a state. And on R1, we'll say do show IP mroute VRF C1 239.10.10.10. And if you look at it, this is just a placeholder, by the way. The star comma G is just a placeholder for the S comma G. That's something that iOS does. But this is the S comma G. There is an outgoing interface list because that's where the join came from. But what's happening on the incoming interface side? Well, the incoming interface side is null because this is the end of the PIM boundary. So unless until you could use some other method, in-band or out-of-band, you cannot add an interface here. And when it happens to non-SSM groups, so this S comma G is a non-SSM group. So let me again send some ping, so hopefully those flags populate. And on R6, so R6 should be sure, and let me do it on R10 actually. Do show or show IP mroute 239.10.10.10. If you look at it, it is still in registering state. So it is still trying to register with R6, and R6 is now trying to join the S comma G. So there are no flags of any value here. But essentially what's happening is you're not creating that MLDP LSP here. So if I say do show MPLS MLDP database, you see 4444, you're basically seeing all SSM groups. So all of these are SSM groups, and let's just do a summary so we can see everything together. But if you look at it, all of these start with 232, so all of these are SSM groups. So with iOS routers and Profile 6, they essentially don't do anything to received S comma G states or star comma G states unless until they are SSM groups. But magically, we are still getting that connectivity. What you would realize on the other side, what you would realize when the, and I think I'll leave this one up to you to do, but what's going to happen on the XR1 side, it's going to be the same thing, but it's going to take matters one level further. So you would still send the unicast register message all the way to R8. So suppose you picked R8888 as the RP. R8 is going to send that S comma G entry up to XR1, and XR1 will then convert it into MLDP, and it will send those MLDP, it'll create that MLDP point to Multipoint LSP. Let's see if we can get this done really, really fast, so that way you don't have to do it. But if we do it really, really fast, all we would have to do is, in fact, what I'll do is I'll pause the video, I'll change the RPs on site 4, and I'll be right back. Okay, and that's all I've done. So I've basically changed the RPs. Let's send those pings again from R10 and see what happens this time. So again, sending packets from 10.10.10.10. I'm getting a reply this time from 9999, but the major change here is going to be on XR1. So 9999 should be getting those packets via R8. R8 should be sending the S, G join. So do show IP M route 239.10.10.10. So it is sending that join. It is switching over to the shortest path tree. But on XR1, this is where the major change will be. So if I say do show PIM VRF C1 topology for 239.10.10.10, you can actually see that a join has been sent. So not only a join has been sent, a join has been sent on that in-band MDT C1 interface. So that means we must have created an MLDP LSP for this. So if I say do show MPLS MLDP database, summary, and that command doesn't work on XR, of course. Brief. You can see that I'm sending. So this is 10.10.10.10 239.10.10.10. Let's just take a look at the long form. Here it is. So this is a non-SSM S, G group. So if I say do show PIM VRF C1 range list, just to make sure I'm not doing any subterfuge, the SSM range is only 232/8. So this is not in the SSM range, but you're still creating an S, G MLDP for this. So this is what happens. One side is completely magical. The other side is working because of static mapping, but it also has MLDP working within it. Now, that is with the RPs co-located with the receivers. Well, what happens when the RP is co-located with the source? I'm not going to bother going to the iOS side this time, because on the iOS side, it just doesn't work. You can try it out. It's not going to work. So unless until there is something new that has been added in the code, that's just not going to work. So in this case, what I'll do, once again, I will pause the video, but I will go and tune everything to use XR2 as the RP. So it's going to be 22, 22, 22, 22, and it's going to be all of the routers in site 4, including the PEVRF, and all of the routers on site 21. So that's exactly what I've done. I've gone to site 4 and site 21 routers, including the PEs and the VRFs, and I've changed their RP to 22, 22, 22, 22. The first thing then that needs to happen is somehow the receivers need to get to the RP, because if the RP does not have A star, G tree, then it cannot really even decapsulate that register message, so not even the magical connectivity. So if, let's see this, if green is PIM, then I need to have that star, G tree get from R9 to R8, from R8 to XR1, and XR1 then has to take it and convert it into MLDP, star, G, MLDP, MP-LSP, and then XR4 needs to receive it. It also needs to change it back into star, G, PIM join. So let's see if that is happening. And one of the easiest ways to check that out would be, if everything went right, is on XR2, we might find an entry for the star, G 239.10.10.10. So let's see this. If I say do show PIM topology 239.10.10.10, actually you do see that I have a star, G entry here, and it looks like a real star, G entry, because it has an exit interface which is 422, which is going towards XR4. So it looks like that might have worked. So on XR4, let's go ahead and see. I'll say do show PIM VRF C1 239.10.10.10, or this should have been topology. And you can see there is a star, G entry here, RPs 22, 22, 22, 22, but the oil has that in-band MDT interface. Now this time it's GIMTD interface. That's the first time I've noticed that. I'm not really sure again what that is. I'll leave that up to you to find out, and I'll find it out on my own. Maybe mention it in a video later. But forwarding IM, I'm trying to look for IM, which is let's see, include IM. In-band MLDP. So it is using in-band MLDP. So there must be an MLDP LSP that was signaled from XR1. So let's go down to XR1. Do show PIM VRF C1 topology 239.10.10.10. And there's definitely an entry. There's definitely an RPF interface, which is that in-band MDT interface. And there is an oil. So finally, let's look at the MLDP database. Do show MPLS MLDP database. And that MLDP database actually does take the star comma G. So that is what is happening now. If the RP was suppose on R1, so suppose if the RP wasn't on XR2, it was somewhere behind maybe even R1. So suppose it was XR 6, so it was right here. What was going to happen was XR1 would still have been able to create that MLDP LSP. It would be star comma G. But when it gets to R1, R1 would basically consider it as 0000 as the source and then the group, and then it would have just rejected that. So I've seen that happen before. I just don't want to spend more time in this video covering something that doesn't work, but that's what happens. So finally, let's go ahead and see if this connectivity is actually going to work. So again, we'll just send some pings. So in this case, again, we're going to go to R10 and we'll send the same pings. We'll say ping 239.10.10.10 source loopback 0. And that was just one, so it may not be the best idea. Let's repeat 5. And this time we do get, we're getting 2. And this is again very, very interesting. We are getting 4 replies from 9999. So one of those could be, so let's try to whittle this down a little bit. One of those is because I'm using the long form. So I'm sending 2 packets out. So that might be causing some of it. So I'm using the short form. So let's use the long form to just dial it down to 1 packet. We'll say ping protocol IP 239.10.10.10. Repeat count, let's say 100. We just want a long repeat count. Datagram size is good. Timeout is good. Extended commands, yes. This is again gigabit Ethernet 2.10.22. Time to live 255. Loopback 0 is the source. And let's send this out. Now still, even though I'm absolutely sure we are sending 1 packet, we are still getting 2 replies back. So what would be the reason for the 2 replies back? If you want to ponder it, pause the video and ponder it before I do the big reveal. But it has to do with the breakage in number 1, the PIM domain, and number 2, how does the SPT switch over work, believe it or not. So let's go ahead and give this a check. So what does happen normally? What happens normally is that R10 is going to do the whole registration process with XR2. XR2 is going to decapsulate the packets, send it down on the star comma G tree, and now we have a viable star comma G tree. And what ends up happening, so suppose this is the multicast traffic, it comes here in a register message. XR2 breaks it down, sends it down the star comma G tree over to R8, and R8 sends it to R9. Once it sends it to R9, what does R9 usually do in this case by default? It does the SPT switchover, right? So it's going to send an S comma G join. Now this S comma G join, suppose this is orange, goes up this way and it's going to follow the path, and everything should be fine. And finally that S comma G join should receive here on R10. Normally what happens with the SPT join is that the router would also prune itself. It would send a star comma G comma RPT prune to the RP, so to basically tell the RP that it no longer requires, so this is only going to happen when the path differs from the SPT path differs from the star comma G path, but it basically informs the router that, I'm sorry, this is not a star comma G prune, this is an S comma G comma RPT prune. So once the router, or once XR2 even realizes that it has received, so it's either this S comma G comma RPT prune, or the RPT realizes that there is an actual S comma G tree now below it as well. So it will stop sending the traffic from the star comma G. In this case, that prune just never happens because what is here in the middle? There is no PIM in the middle, so that S comma G comma RPT prune doesn't happen. So essentially what's happening is R9 is receiving traffic both on the S comma G and the star comma G. So let's take a look at if that is the case. So I'm still sending those pings. And we are still receiving 2 replies back. So once this stops, I'll send it out again. 239, 10, 10, 10. Repeat count, let's go with 100 again. Extended commands, yes. That's the correct interface, and this is the correct source. So let's send it out again, make sure that we are still receiving 2 replies. We are. On R9, let's go ahead and look at the look at the mRoute table. Do show IP mRoute 239.10.10.10. And on this, in this case, it's SJCL. So what is S? So join SPT has been sent. That's right. S is sparse mode. C is connected, and then L is local. So that's fine. Those are all just local flags. And then this is the shortest path tree flag. So 10, 10, 10, 10. But we basically have both of these as forwarding right now. None of those are being pruned. What about an R8? So do show IP mRoute 239.10.10.10. And once again, there is no pruning happening here. What about on XR1? So if I say the same thing, show PIM topology inside the VRF, once again, there is no prune. And finally on XR2, so I'm going to skip XR4 for right now. On XR2, basically this is once again not pruned. So I'm essentially receiving packets on both of those trees. So what would be one of the ways to solve this? If I could disable the SPT switchover, then I should now just see one packet. So if I say IP PIM SPT threshold, and I set that to infinity, and then let me stop these pings here because I'll have to clear the multicast tables everywhere to make this work. So I'll say do clear IPM route 239.10.10.10, and then give this on all of the iOS routers. On the XR, it would be do clear PIM topology 239.10.10.10. On XR1 and XR4, it'll be do clear PIM topology clear PIM VRF C1 topology 239.10.10.10. And again, the same command on XR4. XR2 is already fine. What about R10? So R10 would be the final one. So I'll say clear IP PIM or clear IPM route 239.10.10.10. Just want to make sure on the RP there is no leftover state right now. So I'll say do show PIM topology 239.10.10.10. So there's no interfaces in the O list. So that looks good so far. It knows about the source, but it really doesn't know. I can clear it one more time to make sure. Let's see. Okay, and now I have to sort of wait for this star comma G to come in. So I'll force the star comma G by going to int loopback 0. I'll say no IP IGMP join group 239.10.10.10, and I'll just rejoin it. $239.10.10.10. Just checking things out. What about an XR2? Have we been able to force something? Yep. So now we have a star comma G on XR2. Now, in my mind, what I should see is I should see single pings, because there's not a concept of two trees anymore. So we'll say ping. We'll force it the first time around. 239.10.10.10, source loop back 0, repeat 5, because we cleared the multicast routing tables. So now we are getting those traditional 2 replies, right? So 2 packets, 2 replies, that already makes me feel better, but let's send the long form ping and make sure. 239.10.10.10, repeat count 100, timeout is 2, extended commands yes, interface is this, and the source interface is loopback 0, and then that's it. So now we should then see single packets come in. So as you can see, you can make this work as long as you have XRs. Once again, number 1, it's not scalable. Number 2, this was just basically an adventure in multicast. This is not something I recommend that you spend too much time on. I've spent the time for you, and this is getting to be a rather long lecture. But yeah, we'll bring the demo to a close with this. Up next, we'll be moving to what I like to call true MVPN NG, or true MVPN next generation, which is to say that we will use the BGP MVPN address family to perform all the signaling for us, just like MLDP did in this lecture, but far, far more scalable. Till then, I would like to thank you for joining us and urge you to stay tuned for our next video. Thanks.